test cases and so
Ah,
on.
yes. With Andres? Yeah.
Yeah, with Andres and I guess because I remotely is tough.
Yeah.
Often remotely is not totally obvious, so we'll see. And I guess while the students will be a little
Yeah.
tired at some
Yeah.
point.
Yeah, I think so. They will deserve their weekend. That's okay.
Yeah. We do also.
Yeah, you do. Yeah.
Yeah.
You've done the whole 2 weeks, huh?
Yeah, the whole 2 weeks and the week before in Barcelona.
Ah, yes. Wow. 3 weeks of training.
I begin to know CROCO pretty well.
The details of it.
I did a lot of kind of tool. Spatial schemes, parameterization, polarization, sediment.
Yeah. Every part of it. Boy, you're the CROCO guy, CROCO man now. You will need some vacation after that for sure. and you, Jenny, you will also take some vacations after.
I wish I could, but yeah, I'm definitely gonna have a break this weekend. Nice glass of wine, and then pass out.
We all do that. And Guillaume, he did well as well.
Yeah, it was good. Hands-on, it was well, it ran smoothly. Man.
Yeah, okay.
And actually, on sediment, I was well, people were interested. Maybe not to use it later, but I wouldn't have any questions or anything. I had a lot of questions, and all of them, almost all of them, they did the hands-ons about sediment. And we gave them the choice at the beginning. You can, if you're not interested, you can do something else.
But they did it.
Yeah, did well.
Okay. Interested. So they find it interesting, but we don't know if they will use it. But at least
a few of them actually may use it. Well, I think, for instance, Sini was here.
Yeah.
He's here.
Excellent.
So for him, I think interested from someone else from West Africa also.
Yeah.
Was interested.
Okay, so you made some connections between South Africa and West Africa. That's a very good thing.
Yeah, actually, I was chatting to Cindy about maybe doing a workshop in Senegal in the future, because he was saying that his institute or the institute next door is they've got a new supercomputer. So
okay. Yeah, because he's in Dakar in this new institute. Yeah, that would be a good idea. I will come this time then.
Yeah.
I will find the time. Okay.
Yeah, that would be nice.
Barcelone, tout s'est bien passé.
Ah ouais, c'est bien passé. J'ai eu des retours de Yin qui m'a dit que c'était bien.
Ouais, j'étais surpris. Enfin, je m'attendais un peu à tout, quoi, tu vois.
Ouais, bah ouais.
Cristal et tout ça, mais en fait, c'était bien organisé.
Ah ouais.
Ouais. Il y avait c'était bien organisé, en fait.
D'accord.
Par une autre personne.
Bah ouais, tu vois, finalement, en fait, le chaos, ça donne.
Ouais, ça, mais en fait, c'était impeccable.
Ouais, d'accord. Au niveau des machines, au niveau de.
Ouais, ça allait, ils avaient ramené des machines.
Ouais.
Pas le plus pratique, hein, je pense, mais du coup, ils ont pu faire des trucs et tout ça. Et le niveau des gens était pas mal.
D'accord.
Ouais. Il y avait quelques personnes un peu perdues.
Ouais.
Mais non, mais il y avait des gens de l'Ifremer aussi. Tu avais un mélange sud-nord.
Ouais. Donc, des mecs qui accrochaient, qui tiraient un peu vers le haut, peut-être.
Ouais. Tu avais des gens de Mars, tu avais des gens d'Acri.
Ah, cool.
Et après, même côté sud, tu avais des gens qui se débrouillaient bien.
Ouais.
Tu avais Bamol qui était venu.
Ah oui, Bamol était là.
Ouais.
Putain, j'ai oublié ça. Ah oui, parce qu'il y avait aussi Aram.
Ouais, il y avait Aram, un autre étudiant de Bamol.
Oui, parce que Bamol était à Paris. C'est vrai qu'il est. Je l'ai vu à Paris, en fait. Ouais. D'accord.
Il se débrouillait quand même.
Ouais.
Il y avait un étudiant de Vincent, un Sénégalais étudiant de Vincent.
Ouais. Comment il s'appelle déjà Biran.
Ouais, voilà, c'est ça.
Ouais.
Et donc, ça, c'était pas mal.
Les gens de Mars, c'est des gens qui étaient passés à CROCO ou qui étaient.
Ouais, exactement, des gens de la bio, en fait.
Ouais.
Des gens qui utilisent Bloom.
Ouais, c'est ce qu'on doit avoir dans médiation. Ouais.
Et qui voulaient passer à CROCO. Et après, non, c'est plutôt bien passé.
Bon, ok, bah, tant mieux en fait. On a médié un petit peu trop sur Christelle.
Ouais, moi aussi, je m'attendais à dessous.
Ouais.
Manger quoi que ce soit. Oh, c'était bien.
Ouais, bah,
Et,
c'est bien, ça veut dire que quand même, on peut compter sur eux, quoi. Ouais.
ouais.
Bon,
Et il y avait des Tunisiens aussi, des Tunisiennes plutôt,
ouais,
du groupe
de Monsef. Ouais.
ouais, qui se débrouillent bien en fait, qui
Ah,
sont
d'accord.
plutôt à l'aise avec le modèle et tout ça.
Bon niveau
Ouais,
en codage, en coding. Bon. Ouais,
ouais,
en
je
général, c'est ce que je m'étais aperçu de ça. Les Tunisiens ils peuvent avoir de bons niveaux. Au Maroc aussi, tu peux avoir du niveau quand même. Bon, tant mieux, ça c'est bien. Et ici, alors, les étudiants, c'est un peu
ouais, ça va. Ouais. Première semaine, tu avais un peu de tout.
ouais.
Première semaine, tu as des gens quand même qui ont quelques personnes qui ont quand même ramé, enfin, des gens
Ouais.
qui ont du mal à éditer un fichier. Quoi, tu vois.
Ouais.
Et deuxième semaine, ça marche bien.
Ouais, c'est un peu, ça épure un petit peu le niveau. Bah là, je pense que je vais en perdre certains, hein, c'est sûr, hein, mais bon, c'est pas
Ouais,
grave.
c'est à peu près le taux que tu avais fait au Chili, là. Non?
Ouais,
Bon, ça va. Sur la fin, tu vas en perdre certains, peut-être. Si tu présentes
ouais.
les noms et tout ça. Mais c'est bien, quoi. Ouais, on t'a retrouvé. Je t'entends pas.
Ouais, non, parce que ouais, ok.
Voilà, c'est
Ouais.
bon.
Bon, on va espérer que ça n'arrive pas trop souvent pendant les 2 heures.
Ah,
Bon.
ce serait mieux.
Ouais. Ça vient de ton côté ou d'une autre? Ou de
Je
mien?
sais pas du tout.
Bien sûr.
Ici, ça marche pas trop mal, mais quand même pas tout le temps bien.
D'accord, il y a des coupures.
Ouais.
Bon.
Ok. On commence dans 5 minutes.
Ça marche.
Personne, ça marche.
Ouais. On attend encore. Ouais, d'accord. Lionel est parti au fait?
Ah, il est parti hier. Lionel et Guillaume sont partis hier.
Ah, d'accord. Donc il y a plus que toi quoi, qui assure le.
Ah, il y a moi et Fabien Desbioles. Je sais pas si vous
Ah
connaissez.
oui, je le connais un peu. Ouais.
Et tu étais dans son jury de thèse.
Bah oui, c'est comme ça que je le connais. Donc, c'est pour ça que je te dis, je le connais un peu.
Après, il y a plus que nous deux. Il y avait les mecs de Pisquet aussi qui étaient là. Il y avait Christian Été, je sais pas si tu connais.
Ouais.
Et Renaud Persson, qui est le mec qui a été recruté à l'IRD, qui a été recruté comme IA il y a 2 ans.
Ouais. Je le connais pas, enfin je l'ai vu par email quoi.
Ouais,
Mais
mais là, on a
jamais
discuté aussi Pisquet,
Ah,
plus général, un peu tous les trois. Je te raconterai.
d'accord. Il y a de bonnes pistes.
Ouais, sur une bonne volonté en tout cas.
Ouais. Bon, c'est bien. Il y a Lionel qui est à fond sur le modèle de glace, là, il t'a dit, non?
Ouais, il m'a dit. Il y a Eric qui vient
Ouais, c'est lundi.
lundi dans 2 semaines. Enfin,
Oui, la semaine d'après, ouais. Et il avait l'air assez enthousiaste aussi.
ah, mais
Eric.
Eric, il est prêt à le faire sans
Ah
problème.
ouais, c'est vrai?
Ouais, c'est un mec qui
Bien.
bosse bien, il aime bien faire ça.
D'accord.
Il
Bah,
aime bien changer de sujet, quoi, en fait.
ouais. Explorer d'autres choses.
Il connaît bien, je pense que.
Ouais. Ah bah alors il n'y a plus qu'à, parce que Lionel est très motivé. Nous, on peut servir d'appoint et
Ouais, bien sûr.
ouais, bon, bah, parce que c'est assez de bon. Je pense que c'est quelque chose qui va ajouter un petit peu de la valeur, hein, je pense. Ouais. Ouais, ils arrivent.
Ouais, ils arrivent.
C'est pas le quart d'heure toulousain, c'est les 5 minutes du Cap.
Ouais.
Ça va le Cap, tu t'y es fait,
Ouais,
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 c'est sympa. Tu loges où?
on avait des espèces d'appart hôtel là, à
Ouais,
Observatory.
ouais, c'est bien. Comme à Saigon.
Ok. Non, c'est sympa.
Tu as vu qu'il y a Laurent qui n'est pas en grande forme.
Ouais, j'ai l'impression, parce qu'il répond pas aux emails. J'ai eu un mail de Florian qui m'a dit qu'il avait pris le relais, que Florian avait pris le relais d'un projet où Laurent était PI.
Ouais.
Je sais pas, ça doit pas doit avoir un truc.
Et il a une sorte, comme il explique, une sorte de burn-out, j'ai l'impression.
Ok.
Donc,
Ouais.
il est avec des
Mais
crises
ouais.
d'anxiété, des choses comme ça. Donc, je pense qu'il y avait trop de choses.
Ok.
Donc, ok.
Ok. Donc, ouais, je pense que là, on va pouvoir commencer.
D'accord. Je partage mon écran.
L'écran.
Je peux partager directement. Ouais, non, je fais ça. Tu l'as là?
Oh, I think we must just drag that window to the screen.
Okay.
So let me do it. Go. So is this so big?
Tu es en plein écran, Patrick, ou...
Là, je suis en plein écran, ouais. Ouais. Et ça dit you are screen sharing.
Ouais, on voit de l'autre côté. On voit, ouais.
Sorry.
Ah, vous voyez?
Ouais.
Ok, je vais le remettre.
I need to get the faces. Usually you can, there's an option to it's not black screen, but we like remove this one. Yeah, is that okay? Or maybe
Je peux réessayer, je peux arrêter. Ah,
ouais, non, c'est bon, je pense. Que
c'est bon? Ah, d'accord.
Ouais, je pense que ça va être bon.
that's good.
Ok, c'est parfait pour nous.
Ok.
It's good. Yeah.
Okay. So this morning, the last class, it's about non-hydrostatic physics in CROCO. So everything is remote. So we first have 2 talks from Patrick Marchetello. So Patrick is, you may know him, he's pretty famous. So. And he's working at Legos in Toulouse, like Lionel, Guillaume, Serena, and I, and working on a very wide spectrum of topics. Patrick can go.
Okay, thank you, Rashid. And thank you, Jenny, for organizing this nice training and the whole CROCO team for helping. I've been following some of the courses last week, and I think it was very exhaustive, very rich. I hope everybody enjoyed it and it was useful. This presentation is is a little bit advanced on non-hydrostatic CROCO. I think that you might not understand all the details of what I'm going to present, but I don't think you need all the details in order to use the model even in its non-hydrostatic state. But it will be useful, I guess, that you hear some of these details, and maybe you can keep that in the back of your mind and use the slides again if you want to refresh it. So I have a little plan here. The contents is I will start with a short introduction, and then I will spend some time describing the non-hydrostatic solver. This part is a bit technical and difficult, but at least if you understand the main ideas, that I will be happy with it. Then I will show some various applications of the new solver. And then we can have a little pause here. I think it will take about an hour. In the second part of the presentation, I will present in more details a particular application for surface gravity waves and nearshore dynamics. And then some thoughts about numerical methods, because I think they are important when going into very small scales, as we do now. And then I will finish with a short conclusion as well. Okay, so as an introduction, I think it is useful to look at the spectrum of processes in the ocean. So far with CROCO, we have been working on quasi-geostrophic dynamics and up to the sub-mesoscales, basically up to 1 kilometer scale. This is an example here that shows using AGRIF how we got to the sub-mesoscales. And I think with CROCO now we are quite good with this kind of applications. The challenge now is to go to smaller scales. We have been making assumption that going to sub-mesoscale was almost enough, and that everything that is below the sub-mesoscales will be easy to parameterize, and there will be not much influence on the larger scales. But it turns out that it's not that simple, and we need to better model the processes that are below these scales, because they can have a strong influence, for example, on mixing of water masses with various applications. So when we go down the kilometer scale, we reach a range of scales where the vertical dimension is similar to the horizontal dimension. And this is when vertical acceleration starts to have to play a role. And that's when generally we think that we entering a new regime that is non-hydrostatic regime, because the hydrostatic assumption is no longer very accurate. In this range of regime, we can find the strong internal waves, some heterostrophic instabilities, and then going further, another range of instabilities in the stratified turbulence area. And then further down the scales, the inertial zone, where the instabilities are no longer playing a very important role, but the eddies are breaking into smaller and smaller eddies until they get dissipated by molecular diffusivity, dissipation. Sorry. When we are in the upper range of the non-hydrostatic regime, we generally think we are in the RANS zone, that is the Reynolds average Navier-Stokes equations. I will talk about it a bit more after. And we still need some parameterization. And then when we get to the inertial zone, this is the large eddy simulation zone, where in principle, we don't need as much parameterization, and we think we model the processes almost directly, but not quite. So in order to get into this regime, we need a new solver. We need basically to upgrade the model so that the equations of the model can solve these problems. And this is what I'm going to present now. The non-hydrostatic solver There are two methods that have been implemented in CROCO. One is the pressure correction method for incompressible equations, but the method that we have favored so far is the compressible approach, which I will describe in more details. So the principles of the non-adrostic solver resolve around the separation of the pressure. We can separate the pressure into the surface atmospheric pressure plus the hydrostatic pressure and another type of pressure, which is the non-hydrostatic pressure. This hydrostatic pressure is the one that is involved in the in gravity waves. That is, the gravity waves carry the hydrostatic pressure signals across the ocean. The non-hydrostatic pressure, that is named Q here, is carried by the sound waves. Okay, in the ocean, these sound waves are very fast, and in general, we tend to think that they can be approximated as infinite. In this case, we use the Boussinesq equations to describe the non-hydrostatic pressure. If we consider that they are finite, as it is in real life, then we have to solve the full Navier-Stokes equations. So these two types of equations are the two types of implementation that have been done in CROCO. With this one, the Navier-Stokes equations being the one that we tend to favor, and I will show why. So the first type is the pressure correction method for incompressible ocean, and this was developed by people in Brest, in France, and at UCLA in the US. And this is the method that is the most used for the ocean, because the ocean is incompressible with good approximation. So we tend to think that the Boussinesq equations are natural for the ocean that has a fast sound speed. To get into more details, I present here the linearized equations in just the X and Z plan. So there's no Y dimension here. So the equations become quite simple in this case. So you have an equation for U, for W, and then a continuity equation for volume conservation. So that's the incompressibility assumption. And then you have an additional term compared to the usual hydrostatic equations, which is a pressure gradient in X and Z, non-hydrostatic pressure gradient. So the way it works, the way we solve these equations is that first we look for a solution for the hydrostatic equation, which is a temporary solution that is shown here. It's U tide and W tide. And this solution is not conserving the volume. It doesn't verify the continuity equation. So the full equation will verify it, and it can be written that way by adding the pressure gradient. Then, when we take the divergence of this flow, we get this equation, which is a Poisson equation. And to solve this equation, we need a Poisson solver. So you can see that this equation says that the non-hydrostatic pressure is a result of the divergence of the flow when it's calculated directly from the equations. The particularity of this equation is that it's a global equation. That is, all the points of the domain needs to be solved together in one solver. And this is a challenge for parallelization. So that's one first negative aspect of this method that has been pointed out many times. Then there's another problem with the method, and the problem comes from the fact that we use a split explicit time stepping in which the flow is divided between the depth integrated flow, the barotropic flow, and the baroclinic flow that is the complementary. So the barotropic flow is integrated in a fast time step because it is a faster component, and the baroclinic flow is integrated in a long time step, in a slow time step. So that's fine, but why is it a problem for the solver? The problem is that when you compute the barotropic equations, you get at the end a value for the barotropic flow, and this value is used to correct the hydrostatic solution. But then we want the non-hydrostatic solution, and we need to remove the divergent part using the Poisson solver. When we do that, at the end, the barotropic flow, or the depth integrated value of the total flow, is no longer equal to the barotropic flow that we calculated at the beginning. And that is called a splitting error. And it's very difficult to solve that. Splitting errors can lead to instabilities and blow-ups, so it's not something we can afford. And one solution that has been found to remove that error was to change the boundary condition for the non-hydrostatic pressure from Dirichlet to Neumann. And in this case, we get consistency between the fast and the slow part of the computation. The problem is that we then get the wrong boundary condition for surface waves, because this boundary condition at the surface for the non-hydrostatic pressure is the one that is needed when you want to solve surface waves accurately. So here are two problems with that method. An alternative that could solve these problems is to account for acoustic waves fully in a compressible approach. And we join here the thoughts of Dukovitz in 2013 already, when he said that acoustic waves, they might be negligible entirely in our computations, but the effect of the approximation may be a problem. So why not solving these acoustic waves? The way we can approach the compressible equations is by separating the density this time using a Taylor series into the density that is used in the hydrostatic model plus perturbation to this density, which is the product of the delta P here, which is Q, which is the non-hydrostatic pressure, by the inverse of the sound speed squared. So our separation of pressure is now written as PA plus hydrostatic pressure plus the product of the sound speed squared times the density perturbation. And this will be the variable that will be solved in our new equations instead of Q. More exactly, these are the new equations. So you see they look a lot like the previous equations, but for the use of rho F, the fast density perturbation instead of Q. The difference now is that we have a correction to the non-divergent that is local. It is instead of the Poisson solver, which is a global solver, we can correct the need for an equilibrium of compressibility. We can do that locally, and in terms of computation, it's much more efficient because we don't need an elliptic solver in order to solve that problem. So for parallelization in particular, it's very convenient. Then also we don't have a problem with the boundary condition at the surface because this is local computation. We don't alter the barotropic mode. so we can solve surface waves. The problem, of course, is that acoustic waves are fast. They are about 1,500 meters per second in the ocean. So that will pose a problem of computational speed. And we need to find solutions to lower the stability constraint. So one way to do that is to compute the acoustic mode in a smaller time step together with the barotropic mode. Another way is to use implicit methods in the vertical for vertical fluxes, because they are the ones that usually are the most constraining for stability. And then a third argument is to use to decrease actually the sound speed. We don't need to use 1,500 meters per second all the time for the sound speed. All we need is to have a sound speed that is at least larger than the shallow water phase speed. That is the phase speed of the barotropic equations. And if we do that, maybe the acoustic waves will not be solved very accurately, but the non-hydrostatic physics at scales a bit larger than the acoustic waves, they will be solved properly. So in terms of scalability, this is to show the difference between the two approaches, the global with the pressure correction and the local with the compressible approach. The idea is to see how the model performs when the number of processors is increased. For that, the criterion that we use here is the speed up, which is the time of the simulation for a number of processors divided by the time of simulation for when we double the number of processors. If we have very efficient scalability, we should have a speed up of 2. Each time we double the number of processors, we should reduce the simulation by as much. So here in the plot, we compare the compressible approach in red and the pressure correction approach in blue. And you see that with the incompressible approach, the speed up is always lower than 2, and sometimes much lower than 2. And this is the this is the demonstration of poor scalability. In the case of the compressible approach, the speed up is at least equal to 2, and sometimes even larger than 2. This is called superscalability because in this case, the use of memory, of cache memory in particular, is improved when dividing the domain into subdomains for parallelization. So this is an important argument for using compressible models instead of incompressible models. Maybe I forgot to mention that CROCO is so far the only model that uses the compressible approach in the ocean. It is, of course, very widely used in the atmosphere because the acoustic waves are smaller. They are 300 meters per second. But in the ocean, they have not been used before, and this is the first model that can do that. And we are trying to demonstrate that it is very useful. I will try to illustrate that with some applications that are quite various. They go from surface waves to internal waves, ADs and instabilities and mixing and nearshore circulation. But for nearshore circulation, I will, as I said, use a separate part of the presentation. Okay. So when we first developed the non-hydrostatic solver, we needed to do a test, a simple test, to make sure that the the solver was working the right direction. So this simple test is the tank, and it's still there in CROCO. And I think in the tutorial with Andres, you will learn how to use that test. So the idea is to have a tank that moves and generates a sinusoidal signal that oscillates with a standing wave. In CROCO, we just initialize the standing wave with a slope, and we let the wave equilibrate. So this wave is not unstable; it's just oscillating. And we know for this kind of experiment, we know the analytical solution, both for the hydrostatic equations and for the non-hydrostatic equations. So here the resolution is 20 centimeters for a domain that is 10 meters high by 10 meters long. And these are the initial conditions. So first, I will show the hydrostatic case. And in this case, which is not very realistic because the tank is really non-hydrostatic, but we can compute a hydrostatic solution. It will be a solution of the shallow water equation, which is waves that are non-dispersive, sorry. And on the right, I show the solution in black that you don't really see in full black, the analytical solution for the hydrostatic case. In red, it's the numerical solution for the hydrostatic case. And in a dashed line, you have the analytical solution for the non-hydrostatic case. Obviously, the hydrostatic case is working, the hydrostatic model is working fine and reproducing exactly the analytical solution. So we have a test here of of the fact that we didn't break the hydrostatic model, which is always good to check. Then, of course, we want to see if we can do as well with the non-hydrostatic case. And this is the solution. In this case, we have a dispersive wave, which is the surface wave, because surface waves are dispersive waves. That is different modes have different wave phase speed. And also the period of the waves here is lower. Before we had 2 seconds, and now we have 3.6 seconds. If we compare the solutions, the non-hydrostatic solution is now closer to the analytical non-hydrostatic solution, which is what we wanted. And this is true for the free surface, for U, and for W as well. With W getting smaller with depth, because surface waves are evanescent waves and they tend to be smaller as we go down in depth. Okay, so this first test case is successful, and that's a prerequisite to go further. So the next test case that we tried was the internal soliton. And this test case is also something you can try later. It is still in a tank with 2 dimensions. This tank is 6 meters long, and it's quite short in depth because it's only 29 centimeters. This time there's a strong stratification, and when initializing the stratification with a slope, there is a propagation of a soliton that is generated. And this soliton that you see here, so this is one moment of the soliton, then it will bounce on the wall and then go back the other way, and it's generating some oscillations, a trend of oscillation behind it. So we don't have an analytical solution for that solution, of course, but what we do have is a set of simplified equations that are called the KdV equation. They are written here. The KdV equation are simple shallow water equation, except that there's a term for propagation. There's a nonlinear term that is responsible for the steepening of the soliton. And then there is another term, which is an order 3 derivative, which is responsible for dispersion. You note that when you have a derivative of a variable at an odd order, like 3, it is dispersion generally. If it's second order, it will be diffusion. If it's third order or fifth order, it will be dispersion. This is a general truth. So here the soliton can maintain its shape because there is a balance between nonlinear steepening and dispersion. And the model is capable of doing that balance, and it reproduces quite well the experiment, the physical experiment that was done by Horn et al. That we see on the right here. Actually, the internal soliton test case is copied on the physical experiment that was done by Horn et al. In 2001. So this is also a good checkup that internal waves and solitons are reproduced accurately in the model. Next, we go to turbulence, because that is also one thing that we want to be able to do, resolving turbulence below the sub-mesoscale range. So we have some test cases here too. We don't have analytical solution for turbulence, of course, but we can compare to other large eddy simulation models or physical experiments again. One test case that was run and published in the paper by Penne et al. Is on the Kelvin-Helmholtz instability. This is an instability condition that occurs when, in a stratification, the buoyancy, that is the difference between the light layer and a dense layer, is not so strong that the shear cannot break it. So the shear is stronger than buoyancy to have instability for Kelvin-Helmholtz. This is an animation that shows it. So in this case, you have a light layer above and a cold layer and a dense layer below. And the shear makes this layer roll up and generate smaller scale turbulence, but they can also merge and generate larger scale roll-ups. In this paper, the goal was to measure the degree of mixing by the Kelvin-Helmholtz instability in 2 dimensions, but also in 3 dimensions, and with varying various parameters such as the resolution and stratification and other parameters. So this is something that can be used now with CROCO. Another way of producing Kelvin-Helmholtz instability is in the lock exchange experiment, which is also called the gravitational adjustment experiment or test case. In this case, we have the dense layer separated from the light layer by a wall at the beginning, and the wall is released, the separation, and there's gravitational adjustment of the front between the 2 layers with a speed that we can estimate, and it's actually equal to half the gravity wave using the G prime gravity, and that is a function of the difference between the density. That is the reduced gravity. So we can check that the progression is right, but if the shear is strong enough compared to the buoyancy, then you will also generate Kelvin-Helmholtz instabilities. And then we can compare that with physical experiments to see that they are shared properly at the right with the right energy. These are still academic test cases. There are other cases that were done by different people, some in Germany, some in the US. One was to reproduce the Ekman layer. So if you remember, the Ekman layer is this layer with a decrease following of the flow following a spiral when the wind is blowing on top. So the mechanism for this Ekman layer is shear instability, but with a Coriolis force that is strong, and it produces the spiral. So we checked with other well-known large simulation models that the model was doing the right processes. Then the model was also applied to some mesoscale vortex that were shedding inertial and symmetric instabilities. So this is an experience of how does the mesoscales produce energy down towards the smaller and smaller scales. This is one of the strong objectives of oceanography nowadays, is to explore how the mesoscale is behaving when we can resolve all the instabilities that are heterostrophic. Another kind of heterostrophic instability is the gravitational instability that allows convection. And in this test case, we used, I think it was, yes, it was a Chinese researcher that wanted to model hydrothermal plume. That in this case, a very hot water is introduced at the bottom, and by convection wants to lift up to the surface and generate convection. So we were happy to see that the model was also capable of generating convection, and we could compare that with other models and with the observations. Another area of application is for the interaction between waves and currents. In particular, there is something interesting that is called Langmuir turbulence. Maybe you heard of it. It's cells at the surface that concentrate material or remove material from some of the parts and concentrate it in others. And you see this the expression of these Langmuir cells at the surface of the ocean, because along the lines of concentrations, you have streaks of smooth water because of concentration. And then in between them, you have divergence that are not really seen from the surface. You can see that also looking at images of sargassum that can be concentrated in streaks by Langmuir cells. So there was this work by Hermann et al. In Poland, trying to reproduce the action of these Langmuir cells and the turbulence that is associated with these cells for structuring fragile ice. Fragile ice is ice that is not completely solid, but between solid and liquid. And this is something that is commonly observed in high latitude. And so if we can produce the Langmuir cells, we can model these things. The way to produce the Langmuir cells is to introduce in the model a vortex force, which is the product of the Stokes drift, that is the drift produced by waves. It's a Lagrangian flow, and it interacts with the vorticity of the Eulerian flow that is forced by the wind. So when the waves and the wind interact, they produce these cells. We introduced the vortex force in the model, and the generation of Langmuir turbulence was possible, and the accumulation of fossil ice was demonstrated. This was done with a resolution of 3 meters. Okay, there's another area of application. It's nonlinear internal waves, and that will be presented by Laurent Robout after my presentation. So I will not describe too much this application, just maybe show you an animation that was made by Lucie Bordois 4 years ago, where you see the release of a front that generates internal soliton that looks a lot like the observation of internal soliton from space. I will let Laurent describe in more details even that one. What we are trying to do, so going in larger scales, we want to do multi-scale modeling, which means that we want to be able to produce the very small scales that I've been showing before, but while also generating the larger scales that will trigger the smaller scales. So this will be done with AGRIF in a nested grids, and in the future it will be done with something we call multi-grids, that is a more automatic generic way of generating smaller grids in order to go smoothly from large scales to smaller scales. Then there's another kind of application, that's the last one, which is actually a different kind of application. It's for the large scales, for the large scale equatorial domain. In this case, it is not the non-hydrostatic pressure that breaks the hydrostatic assumption. It is the Coriolis force, actually the one that we generally neglect and that we call the non-traditional Coriolis force, that is written here. So if we write the equations with this non-traditional Coriolis force, we have one of the term that is in a hydrostatic equation, and this one breaks the hydrostatic equation, and that's why we call these equations quasi-hydrostatic rather than non-hydrostatic. So it's a bit different from what I've been showing before. It's a different set of equations, but I think it's useful to mention that we have now this set of equations available as well, and people that work with CROCO on equatorial dynamics tend to use these equations now. It was implemented in CROCO while working with people in Stanford, and this is an example of equatorial waves using hydrostatic or quasi-hydrostatic equations, and it's compared to the MIT GCM model, which has the same capability, except that the MIT GCM model is not using sigma coordinates, but z coordinates, and also it is using numerical methods that are of lower order than in CROCO. So you see that you have some noise near the bottom for both the hydrostatic and quasi-hydrostatic solutions, and also the wave energy has less magnitude, which was for us a good result also. Okay, I think I can stop for 5 minutes here. If you agree.
Yes, we can do this. We can take questions if there are.
Yeah.
If there are not totally. Do you have any question? But they look a little lost when you complete.
Yes. Yeah. I'm not too surprised. I think they would need time to process all this. Okay.
From Jenny.
Yeah, I mean, I guess it's So that was really interesting. Thanks, Patrick. You really opened my eyes to a whole new world in CROCO. So I was interested in evaluation, and at these scales, I guess you're even pushing the limits of what we can observe.
Yes.
And I guess in a lab and the sort of idealized experiments, it might be obvious how you validate, and you showed some examples of that, which was really good and instructive for me. How would one do that in a real case scenario? How would you evaluate a non-hydrostatic solution?
Yes, it's a good point, because we really want to apply the model to realistic cases. Usually it's not done that way. Usually these kind of models are only used in laboratory experiments with like a cube, a domain that is a cube, no topography, no coast, etc. And that makes it a bit easier to maybe to validate. In this case, we need to go towards a new kind of observation, I suppose.
Yeah.
And we want to improve, for example, the satellite observation that goes into a smaller and smaller resolution, but also the in-situ observations. And both the modeling and the observation needs to go in the same direction of improvement. So, yeah.
Yeah. Okay.
But we can do quite a lot of things also with laboratory experiments in order to validate what we're doing. And then we have to trust a bit the model once we are validated, I guess.
Yeah, actually, we have plan of there are people doing things with a cross comparison between a CROCO and lab experiment at lab experiment at a large scale in a Grenoble and so on.
Yeah.
So,
yeah.
That must be quite fun. Experiment and modeling at the same time.
Yeah. I will just break 2 minutes to refresh my head. I'll come back.
We'll do a small break, so we want you 10-minute break.
10 minutes?
Yeah, okay. So we come back at 10:30?
Yeah, that's good.
Yeah.
Okay, thanks. See you soon.
Okay.
Yes. And it's
Hello, I'm back. Rashid, are you here? Hello.
Oh, I don't know if the mic's on, so.
Is Rashid or Jenny around?
No.
Okay.
Yes.
Okay. Yeah.
Okay. Hop.
Okay, so I think to see. Is everybody here? Shall we start? Is it good? Who's missing? Kevin. I think we should start because it's already 3 minutes past. Hello,
Okay.
Patrick. We're all back now.
Okay.
I think you can maybe start. Let me just change the setting. Okay.
Okay, thank you.
Thank you.
Let's get started. Okay, this is the second part of the presentation then. I will present more details. One application which is for surface gravity waves and nearshore dynamics. I think it is first because it's the domain which I tend to work mostly at the moment, and it is in high demand by a lot of people because it is find to be useful for society in general. A lot of the problems arise at the coast and need good models to solve this problem. And it's a very nice way of applying another static model. Okay, so the problem I will tackle more precisely, it's the one that has to deal with rip currents and surf zone eddies. So when the waves travel from far and they break on the beach, they tend to produce currents and turbulence at various scales. So this image is an illustration of all the scales that are present. There are at least three that we can see. One is the usual what we call flash rips, that are the larger scales of rip currents on the beach. But then there is also a second scale that we can perceive here with turbidity signals that are sometimes called mini rips, but they are really not well known. And this will be the subject of this part of my presentation. Then you have smaller scales even, which comes from the breaking of waves into turbulence. And it is illustrated by the foam generated by the waves. And this spectrum of turbulence, we don't know it very well. It is not modeled always very accurately, although most models are focusing on the flash rips, which are the larger scales. But below the flash rips, we don't know much of it. And it's quite important for many things. For mixing of pollutants, where the pollutants go when they are rejected in the ocean, where does it go along the shore, where does it exchange with the ocean, with the continental shelf and further? This is an important question. Another question is the surf hazard. I put here on the left results that was based on 10-year average in the US that shows the weather and marine related deaths each year. And as you can see, rip currents are the most important cause of death each year in the US. Before flood, tornadoes, lightning, even hurricanes, and much before sharks and even jellyfish. So in many countries, and not only in the US, people take rip currents very seriously as a cause of hazard. And one part of our work as modelers is to respond to this demand. So there are two kinds of rip currents. So I was talking about flash rips, but the main type of rip current that is generally studied is the one that is called the channeled rip current, because it is associated with a channel in between sandbars, for example. If you have the breakers coming from the ocean, they break on either side of the channel, on the sandbar, and they feed a rip current that goes back to the ocean in between the sandbars in the channel. This we generally model with wave average equations. 10 years ago, we only had two-dimensional models that had the wave average components in it. And in the last 10-15 years, we had a robust set of three-dimensional equations that were also implemented in CROCO. And using these wave current interactions, we could model rip currents, channel rip currents with quite good accuracy. Here, we didn't use the non-hydrostatic equations, but if we want to explore the other aspect of rip currents, which are flash rips, we need to address the fact that waves are not always long crested, like on the left here. They generally appear as short crested, and the short crested waves are due to the fact that waves come from various directions, and they interact, they interfere. Sometimes they interfere positively and sometimes negatively, and the result is these short crested waves that have the capability of generating flash rips on their own. So in order to study these flash rips, we need to have a model that can solve waves and therefore that are non-hydrostatic. So the first type of non-hydrostatic models that are used for modeling flash rips, they are two-dimensional. They are called Boussinesq models. They are actually, these Boussinesq models, very close to the KdV equations that I was mentioning before for modeling solitons. They are also, except that these ones are two-dimensional in X and Y. So this is an application by Feddersen in Scripps Institution of Oceanography. They were able to generate short crested waves at the offshore boundary, the waves propagating to shore, and generating by a vorticity, which is related to the differential of breaking, some flash rips that are showed in the vorticity on the right. So these models are very efficient in generating these flash rips. The rips are very strong. Are they accurate? When to know if they are accurate, we look, of course, at measurements, and this, in a way, responds to the question by Jenny before. For the nearshore area, we have some amount of measurements that are incomplete generally, but they can provide. They can be very useful in order to validate our models. In this case, this is what I show is a spectrum of energy, a frequency spectrum at some point in the surf zone. And what we see is the energy of the swell on the right, with scales of a few seconds, let's say 10 seconds. Then you have infragravity range in the middle, which is about 1 minute. And you have what is called the very low frequency range, which is the range of the flash rips. It's about 5-10 minutes. And in the paper by Feddersen, he showed that the flash rips in a model were much too strong. Their energy is much too high compared to the observation in the black curve here. So it raised the question to us whether these models are complete and are accurate for modeling these recurrence. So we wanted to apply CROCO on it. First, we can we can wonder if CROCO is the best choice, because CROCO is a free surface model. It cannot break the surface. Before, a lot of models for modeling the breaking of surface waves were what was called volume of flux models, that are models that written in the Cartesian coordinate that solves the evolution of the free surface, a free surface that can actually break and separate, like on this simulation. So it solves the breaking turbulence as well. But the problem is that these models are very expensive, and we can only apply them on one wave on a short time scale. We cannot apply it for a full beach, and this is what we wanted to do. So nowadays, free surface models have emerged that are used more and more for nearshore simulations, free surface 3-dimensional models, which we could classify in the Reynolds average Navier-Stokes equation models. And there are at the moment 3 models that could be arranged in this category. Besides CROCO, there's NHWave, which is a US model, and SWASH, which is a model developed in the Netherlands. In this case, the turbulence of the breaking waves is not solved explicitly, but the turbulence generated by the currents is solved explicitly, including the 3-dimensional turbulence. So we developed CROCO for this kind of problems, and we first needed to validate CROCO on simple test cases. Again, we use tanks, lab experiments, in which a swell is propagated from one side to the other and produces waves that can break. And we have, in some experiments, like in the Globeck experiment, a very high resolution measurement of the waves, so we can compare all the aspects of waves all the way from the offshore zone to the shoaling zone when the waves increase to the breaking zone. We compared CROCO with these measurements, and the results were quite satisfying. Here, what I show on the right is a measure of for both the sea level and the undertow of a few moments of different orders. Here it's the wave setup, that is the mean sea level. Below is the significant wave height, which is the variance, basically. And below is a third moment that are skewness and asymmetry. Skewness is what you have in the shoaling area when the waves become very pointy and their shape is skewed. Asymmetry is what you get in the breaking zone when the waves become like seesaw, put forward. And both skewness and asymmetry is well reproduced in the model, as well as the setup and significant wave height. This is true also for the undertow, that is the current generated by breaking that goes towards the offshore zone. All the moments of this current are also well reproduced, so that is quite satisfying. Another validation was done with a large-scale flume experiment. This is also in Delta S in the Netherlands, where they have this kind of devices that are quite unique in the world. In this case, in the LEAP experiment, we wanted to validate the use of turbulent model in order to be sure that the right amount of mixing is produced by the breaking when the wave breaks. One way to validate this aspect is to look at the profile of the currents. If the mixing by the turbulent model is too strong, then the profile would be smooth, and it will look a bit like a two-dimensional model where there's no profile at all almost. If the mixing is not strong enough, then the profile would be very sharp and very unstable, so quite unrealistic. So we find out that with the usual turbulent model in the GLS approach, I don't know if you have heard of that in the last couple of weeks. We have a few turbulent models in CROCO, and the GLS approach allows to use either the K epsilon model or the K omega model. And the K omega model was giving the best performance. Fortunately, we didn't see that much sensitivity between the models and parameters of the model, and with different resolution, the results looked quite similar with just a few, a bit of variation. So it's comforting for the capability of the model to represent the currents generated by the breaking waves. It is also comforting for the robustness of the results. Next, we, of course, wanted to apply the model to a three-dimensional case. So we had the opportunity of a campaign of measurements in Benin, in the Gulf of Guinea, where measurements were taken along a beach that had a nice swell, very clean swell, and also along shore by the beach was had no variations along shore, so it was almost an ideal case in a way, even though it was a real case. So it was perfect for testing the ability to produce flash rips because we didn't want reefs that are formed by topography. So here I show an animation of CROCO producing waves, short crested waves, and breaking at the beach and producing foam that is represented here by the turbulent kinetic energy of the model. So there's a wave maker at the offshore boundary that produces the waves, and they propagate naturally towards the beach. The resolution is 50 centimeters, and there are only 10 levels in vertical. I will compare briefly two experiments. One is the full Navier-Stokes equation, the full three-dimensional equations. In this case, I show the crusher currents here on the left. In this case, when the wave breaks, they produce an onshore current going towards the beach. And this current, as it reaches the beach, flows again back to the ocean for conservation of mass. And this countercurrent is called the undertow. And it's important, the undertow, because it carries a lot of things, including sediments. Then we make an experiment in which we increase mixing in the subzone, which will mix these currents onshore and offshore, and as a result, there will be no crusher circulation. And in this case, we have a model that is looking like a two-dimensional model. So we think it reproduces two-dimensional simulations by usual Boussinesq models. So first, I show actually the results of the two-dimensional model, and you have to trust me if I say that the results in terms of vorticity looks a lot like the results of a Boussinesq model, with very coherent ADs and RIPs that are, of course, two-dimensional, even when it propagates offshore. And this is the result of a full three-dimensional simulation. In this case, the flash rips are still visible, even though the ADs are fragmented, more fragmented. But what is new is the generation of mini rips, which takes the form of a rib structure and appear with smaller scales. So when we try to analyze this instability, we find out that the mini ribs were the result of shear instability, vertical shear instability. It is actually a little bit like this image here, which I show of a wave that breaks. You see the roll. Okay, see it again. You see the roll that looks like the rolls in red here, and then the filaments that cross the rolls that looks a bit like the green filaments. The difference here is that this is the turbulence generated by the wave when it's breaking, and it's of a much shorter time scale than what it is for the instability generated by currents. The space scale for this instability is about 5 meters between the filaments, and the time scale is 40 seconds. So here, for the breaking waves, it is more like it is lower than the period of the wave. So this is turbulence at small scale, and this is an intermediate scale of turbulence, which will cause the mini rips. The result is compared also with drone images that we had during the campaign, and you can see on this drone image the turbidity that tends to reproduce the mini rib structure, the rib structure, and this looks much more like the 3D simulation than the 2D simulation in which you only have the big flash ribs that tends to dominate the solution. So the three-dimensional simulation is more realistic in this case for sure. We can go back now to the frequency spectrum that I've been showing before. We have compared the spectrum to measurements in the surf zone, like it was done by Feddersen. And in this case, again, like in the case of Feddersen, we find that the 2D model has too much energy for flash ribs, while the 3D model has the right amount of energy. Also, there was a deficit of energy in the infragravity range, which is also true actually in the Feddersen case, while the 3D model, because of the mini ribs, have a larger amount of energy in this range. So this range doesn't contain only infragravity waves, but also the mini ribs. So this is the end of my presentation of the nearshore dynamics. It's just an example. We have done other applications in the nearshore, including for sediment modeling, but I will not present it here because I don't have time. But I would say a few words on numerical methods, because I think they are important when using CROCO on such small scales. I think you have had some review of numerical methods with Serena last week. I will just remind you of the main parts. In CROCO, like in all finite differences model, we use a discretization of the advection scheme, or all the terms of the equations, using finite differences. We therefore model derivatives using points that are around the points where the derivative is computed. The example I'm taking here is for the linearized one-dimensional advection equation here that you have seen with Serena. If I take the simplest possible scheme, which is the centered second order scheme, taking the points just out next to the point of interest, the point G, then I get so this form for the advection term, and using a Taylor series expansion, we can develop this term and compute its error. So this term is equal to the actual mathematical expression of the advection term plus errors. And there's one leading error term, which I will use for my demonstration in the following. So in terms of centered schemes, the one we just saw was the second order center scheme. So I recall here the error, the dominant error, and I'm showing the application of the simple advection scheme on the advection of a Gaussian shape, a Gaussian function. So this is the initial state, and this is the result after a certain amount of time. What we see is the generation of wiggles, of oscillations from that are quite strong from the Gaussian shape, and this can be understood by the formulation of the error. This error is proportional to the resolution delta x squared. So it is why we call it second order, because the error decreases as the resolution decreases at the power of 2. And then it is also proportional to a term that is a third order derivative of u. And this, if you remember, because if it's order 3 on odd order, it is a dispersive term. It means that not all the components of the Gaussian function will propagate at the same speed. So it will disperse waves as it is advected. All center scheme as dispersive. But when we go to higher order scheme, taking points that are further away from the center, then we can reduce the error because it's now, for example, here a fourth order scheme, and there is still a dispersive term, but it's a higher order, and we see the wiggles are still present, even though they are lower. In CROCO, one way to deal with this dispersion that can actually affect strongly the solution is to add a diffusion term that will smooth the dispersive modes. In CROCO, we use choice of having the dispersion terms within the advection scheme, and we do that by not using center scheme, but what we call upstream scheme. That is, we bias the scheme towards the upstream direction, taking more points in the upstream direction than in downstream. When we do that, for example, for the simplest scheme possible, taking only the point G and G minus 1, we get a first order scheme because the error is proportional to delta X. And you see in this case that the error is also proportional to a second order derivative, which is looking like a Laplacian diffusion. So this error is diffusive. And we see that in the simulation of this Gaussian shape. In red, you have the initial state, and in black, the solution after a number of cycles of advection. So the smooth thing with this first order upstream scheme is very strong. If we use a third order upstream scheme, taking more points around the center, like here, we can get a third order scheme because it is in delta x3, and it is proportional to a fourth order derivative, which is an hyperviscosity term. In this case, the diffusion is lower, but still present, but of lower magnitude, and the solution looks much better compared to the initial state. We can show that all upwind schemes have this capacity of exactly cancelling the dispersion term because their leading order error is always diffusive. That was demonstrated in a recent paper. So this is the default choice in CROCO. And we went even further than UP3. We went to UP5. In this case, the error is proportional to delta x5, and the hyperviscosity is of order 6. So that was applied to the case of an ideal MEDI. It's a kind of vortex, subsurface vortex in the Mediterranean, coming from the Mediterranean. What was shown is that just using UP5 instead of UP3, we could double the effective resolution of the model. This is demonstrated by the energy spectrum. That means we get the same amount of energy whether we use UP5 or we double the resolution of the model. And using UP5 only costs about 5–6% more than using UP3. So there's a large gain from using high order numerical schemes, even only for the advection scheme. And this improvement of effective resolution can be seen also for the non-hydrostatic applications of CROCO. I come back here to the Gibraltar test, the Gibraltar application that I mentioned briefly before, and we compared at the same simulation, a 200-meter simulation, with another model that was using low-order schemes at the same resolution. So usually we believe that 200-meter resolution for this kind of internal solitons is two cores in order to model the solitons. With CROCO and higher order schemes, we see that we start actually modeling the soliton and the trend of waves that are behind the soliton, which is not done at all in this case. Just we see just a small signal of it. So here again, the use of higher order schemes improves the effective resolution of the model, even at very small scales. Then upwind schemes are very nice and have nice behavior, but there's one thing that they don't do very well is to preserve monotonicity, and they don't behave very well near shocks. And we have a lot of shocks at small scales, so we needed to correct these schemes for the small scales. Here I show again the results of UP1, which is very smooth for the Gaussian shape. It is also smooth for the square shape, where there is like a very strong shock of the signal. Then using UP5, we do quite well on the Gaussian shape, but as you can see, we generate oscillations here. The oscillations are generated by the hyperviscosity in this case, because the hyperviscosity is inherently dispersive. So even though it is diffusive in nature, near shocks, it can still generate some oscillations. And the only way to correct that is to have special schemes that are nonlinear, because they correct the oscillations when they see it. And one of these schemes is WENO5, another one is TVD. We both have these schemes in CROCO, and you can see that the result is as expected, that the oscillations have disappeared. Of course, there is some remaining diffusion, but the application of these schemes to small scales is much more appropriate. So we talk about shock capturing schemes in this case, and we need them at small scales. An illustration of that in a realistic application is for the Gibraltar problem again, in 2D here. When we use the upwind schemes, which are non-monotonic, we had plenty of oscillations at small scale, and it could even make the model blow up. So we had to apply monotonic schemes expressly in this case. So applying TBD, but the result is the same with WENO5. We were able to remove the oscillations and to run the model as long as we wanted. Another application was for the Kelvin-Helmholtz instability. Here are three cases. The first case is with using a centered scheme for the advection of tracers. In this case, you remember that the center scheme is dispersive numerically, and you see a lot of oscillations, and also the generation of eddies that are not meant to be here. So a lot of eddies and oscillations. When we go for a scheme that is not generating numerical dispersion, but that is not monotonic, we correct some of the errors, but we have still oscillations near the fronts. Then when we use a monotonic scheme, we remove all the oscillations, and only the physical solutions seem to appear here. That is a roll-up with secondary roll-ups along the fronts. So the conclusions of the whole presentation here is that we think we are quite successful in our attempt to design a model for bridging gaps from the quasi-geostrophic regime down to the microturbulence. We are on the path. Not everything is done and settled yet, but we think we can see that the model can be applied in many areas of these gaps between the two large scales. then also we are able to bridge gaps between the oceanic zone and the nearshore zone. Obviously, with multi-grid approach, we will be able to have a smooth transition between the oceanic and the nearshore zones. So that will be to develop further in the future. The compressible approach we find has many advantages: accuracy and performance, scalability. So I've shown multiple tests and applications with good performance. And of course, we need to do further developments, but these tests are very useful in order to guide our developments. And of course, there's room for improving numerical methods and parameterization. So we need to go towards higher order monotonic advection schemes still. And okay, as I said, multi-resolution is one area that we want to continue and improve, and also revisit the boundary conditions, particularly the topography and maybe the substrate like grass, mangroves, and other kind of porous media that we want to use in our applications. So we want to make the model more and more able to be applied to the real world and not only to laboratory experiments. Okay, so I will end my presentation here, and if you have questions, I'm ready. Thank you.
Okay, thanks a lot, Patrick. It was a very nice presentation. So, do you have any question there? Well, not so much, I think. Even Jenny is out of questions.
Well, actually, yeah.
I don't know if Rashid or Jenny are around.
Yes, there's one question if you can.
For the RIP experiments, like what kind of time stick do you use, and what model? How long do you run the model?
So yeah, there's a question about the RIP experiment, about the kind of resolution, space and time you're using, and the kind of experiments, like long-term experiments, super short-term, and so. Not sure.
So you can see. Hello, Patrick, do you hear
I
us?
can't hear you, Jenny.
Okay. That's very strange. Hello? Nicolette, are you in the Zoom call by any chance? Okay.
Still can't hear you.
Strange. I don't know what changed between previously and now. Are you typing your question? The only thing I changed was to plug my charger in. Hello? Hello?
Hello from the home.
Okay.
Hello.
Hello? Sorry.
I still can't hear you. I don't see the chat.
Hello. Can we ask the questions?
Hi, Frederick. Can you hear us?
Well, I'm hearing you.
Okay, Patrick, it sounds like it's just on your side.
Okay. So I want to know if we can ask question.
Can you wait just a minute because we're experimenting?
Okay. Okay, I can read the question. Thank you.
Okay, so there is a first question.
So for the RIP experiment, this one, speaker is off.
No, it's okay. We're hearing.
Really? Yes, my speaker was off. Sorry, it was me. Sorry.
Okay.
Okay. So the question was the RIP experiment. What are the time steps duration? Okay, the time step is very low in this case. It's something like 0.1 second. So nothing to do with the time step that you usually have for regional configurations. The resolution is 50 centimeters, so it has to be proportional to that. Yeah. So of course, we run this kind of simulations for a few hours maximum so far, but it is still much better than for example, the models that I've shown before, like these kind of models that can simulate the breaking of waves. These ones are much more expensive, like a few orders of magnitude. So in a way, it sounds expensive, but at least we can do a full beach here. The beach is like 500 meters long and 250 meters large in this case, the domain, and we can do the whole thing, run the model for a few hours, and do multiple simulations. So we can do a proper study of the whole beach and compare with data. And this with the usual models is not possible to do.
I think there's a question from Frederick online. Please go ahead, Frederick.
Yes. Thank you very much, Patrick, for this presentation. Sorry, I was late, so I joined the meeting after you started the presentation.
Okay.
My name is Frederick Bonu. I'm from Benin. Yes. I am. I am one of researchers who is in charge of the camera system in Benin. Yes, I joined the team in 2016. Yes. At this moment, Serge Tometin was there. I don't know if he's in the room there for the person who are attending the meeting in person. So I'm very happy that our work, yes, have been implemented, used by the CROCO model.
Yes.
Yes, I saw that in the study case, you have had also, yes, data collected from this camera system. So the camera system actually is not working, but we already got, we are getting a new camera system now. So this monitoring system.
Yeah. We lost him. But I think he was mentioning, because we have a member of our group here that is.
Hello?
Yes.
Yes. Sorry, I lost the connection, so I didn't finish already with my comment. So I'm still comment, and after we give just one or two questions after my comments.
Okay.
So yes, so yeah, we are still working not only in Benin but all the whole West Africa, Cameroon, Ghana, Senegal. So we are a network working. We are a group of researcher group working on the implementation of this camera system. I think this is nice that you show this case in Benin, showing about the rip current and also the wave swash in Benin. Yes. Yes, one thing that I want to know.
Maybe I can comment on that because it is also an answer to the question by Jenny. For the nearshore area, it is true that we are developing both new methods of observing the coastal zone and new models. And the video cameras, so the drones, and now also the satellite images. They are accurate enough to show us things that we couldn't see with in situ measurements. And so, well, it's. So what are your questions?
Okay, nice. So now I will jump to my question now to know if it is possible to use CROCO model to do some impact study for mainly like a propagation in harbor port, propagation of wave in harbors, agitation of a wave in the sediment transporter. If we can develop some kind of scenario depending of the morphology of a beach, of a port, how the wave will penetrate to the ports. I want to know if is it possible to do the kind of study of that.
Okay.
With, yes.
Okay. So usually for these kind of problems, they use 2D models like pussiness models, which are relatively cheap to run, and I think they model relatively well the penetration of waves into the ports and the circulation that is generated by these waves. But for example, if you want to study sediments, these models are not suited because they you need a three-dimensional model for resuspended sediment and transporting it in an accurate way. So I would think that CROCO is suited to do that. It has sediment model, so it could be used in a port to transport sediments. Then, if it's only to see how the waves are getting into the port and circulating, maybe a 2D model will do as well and might be cheaper. It depends really what kind of problems you are dealing with.
Okay, thank you. I guess so. Yes, thank you very much.
Okay, thank you.
Do you want to come up here, Cindy, so that Patrick can hear you?
And yeah.
There's one more question from Cindy.
Okay.
Hi, Patrick.
Hi.
Nice to meet you again.
Okay, nice to meet you too. Again.
Relative to my work in the Senegalese area,
yeah.
I see you have one test case in Gibraltar and in Benin. Is it possible to deploy one of these West African case in the model, like one test case we use from a bearing sediment, something like that?
You mean something that so for internal waves then?
Yeah.
It's a question about internal waves. Yes, we have a first implementation of the non-adversarial model for internal waves of Senegal. It was a two-dimensional simulation, relatively cheap because it was two-dimensional, X and Z, and it showed quite nice results of waves interacting with the continental shelf break and then propagating into the continental shelf. And this could be extended to a three-dimensional model, I suppose, and do something similar. But what would be the application in your mind? You would like to see how the internal waves are propagating towards the shore and influencing the water masses, for example? Or is it something else?
Yeah, so yeah.
It
will be just a test case for our ocean modeling course for the students.
Yeah.
To show them how it works in the West Africa.
Yeah, it could be particularly suited to upwelling, the study of upwelling, because usually internal waves are not mixed with upwelling when we study them. We study upwelling or we study internal waves, but the interaction of internal waves and the mixing that produces internal waves with the upwelling process, that I think that has not been studied very much at all. And that could be an interesting thing that could be done in West Africa. Yeah. Thank you, Jan.
Any other question? Well, no more questions. Thanks a lot for time, presentation, and so on. It's a nice way to finish the classes.
Okay.
So we'll move to we're sticking on non-hydrostatic. We'll move to a presentation from Laurent Roublou. So Laurent is So Laurent is working also in Toulouse. It's another lab which is called l'Aéro. It's a lab next door our lab. He's working in a team which is fully involved in development and application of non-hydrostatic CROCO, especially in the Mediterranean Sea and Gibraltar Strait with formation of solitons to tides, topographic direction.
Hi, Laurent. You should be able to share your screen, hopefully.
You hear me?
Yes. Hi, we see you and hear you.
I'm with this guy. I will share my screen and just second. Is it okay for you?
Yes, that's perfect. Thanks.
Okay, good.
There we go.
Well, so everybody can hear me in the room and in remote?
Yes.
Yeah.
Okay. Well, so I'm Laurent Roublou, and like Rachid said, I'm working in Toulouse for CNRS. I'm very glad to be here with you and share some works we have done on the CROCO NBQ module for non-hydrostatic simulations. I will present several applications of this module that have been developed in our group, led by Francis Auclair, in order to study the dynamics of the Strait of Gibraltar. I will thank for starting all my co-authors and the sponsors we had for these studies. So we'll talk about the Strait of Gibraltar. This is this narrow passage between the Atlantic Ocean and the Mediterranean Sea. This is the unique entrance of the Mediterranean Sea, which is a semi-enclosed sea between Europe and Africa. So this strait is bordered by Spain, north, UK, here in Gibraltar, and Morocco, and a small exclave of Spain, in this peninsula of Ceuta. So it features great important economic activities for the countries of both continents, and it is one of the world's busiest waterways. And we have also important defense activities for both continents. So the strait is about 60 kilometers long, with a width of 13 kilometers at its narrowest here. The western end of the strait is located between Cape Trafalgar and Cape Espartel in Morocco. It's about 40 kilometers somewhere there. At the eastern end, you have the Rock of Gibraltar and Ceuta here. and you have about 23 kilometers. So the depth of the strait range between 300 meters somewhere here at Esparta-Sil and to 900 meters in the entrance of the Mediterranean Sea. So if you have a large-scale picture, you have the Atlantic Ocean, the Gulf of Cadiz on the western end, the Strait of Gibraltar, Alboran Sea, and the Algerian Basin entering the Mediterranean Sea. From an oceanic circulation point of view, you have a significant amount of water which is exchanged through this strait to balance the ocean atmospheric fluxes over the Mediterranean Sea. Because of the evaporation and precipitation imbalance over the Mediterranean Sea, the Atlantic Ocean and the Mediterranean Sea have different salinity levels. And therefore, highly saline waters from the Mediterranean Sea flow outward and in depth, and this is called the Mediterranean jet. Whereas less saline Atlantic waters flow inward and on top of the Mediterranean Sea current, and this is called the Atlantic jet. You have also two nice, interesting features, Alboran gyres, which is out of the scope of our talk. And let's mention that all of this is under the influence of the tides from the Atlantic, the Northern Atlantic Ocean. So we will focus only on the small-scale processes that are occurring within the straits with typical length scales of less than 1 kilometer. So as I said, the ocean circulation there is a two-way exchange flow directly influenced by the interaction between the intense tidal forcing from the Atlantic Ocean and the complex geometry of the straits. So you can see here a vertical transect of the bathymetry and the depth of Camarinal Seal here, 300 meters, as I said, and inside the Mediterranean Sea, it's 900 meters. So several small scales contribute to the mixing of waters within the straits. You can see small. Sorry, is it okay? No, so you have small scales amplitude internal gravity waves at the interface of the Atlantic and Mediterranean waters. Here at Camarinal Seal, you can see hydraulic control caused by tidal currents, and consequently, you have this jump. You have shear instabilities at Camarinal Seal. And when the hydraulic jump is released during the inflow conditions, you have an energy propagation eastward, and you can see a train of internal solitary waves. So this the surface signature of these internal solitary waves are classic and can be seen from space. You can see satellite radar SAR imager from ERS-1 or Sentinel-B. You have these large trains from space. You can see them with hyperspectral imagery like MODIS, Ocean Color Sentinel-3 at the center, and Sentinel-2 as well.
Maintenant, j'ai...
Somebody is speaking. Can I shut down the mic? This is spaceborne optical imagery, where you can see from the International Space Station here some trains. This is Pleiad imagery. As well, Pleiad here over the hydraulic jump, and you can see a boat on the sea. And from a boat during the 2002 campaign, we can see this feature from just the boat with your eyes or with a personal camera. So this to study these dynamics in further detail, realistic numerical models is of great help. So you attempt using two-way layer models, like works from Brand and Stierdo. The increase of the computational power led to 3D modeling with increasing vertical and horizontal resolution, explicitly addressing the tidal cycle and the flow characteristics. Some aspects of the strait hydrodynamics could not be well reproduced by this standard numerical model. So this is especially concerning the evolution of the internal tidal bore, where after its generation, the bore progresses towards the Mediterranean Sea, evolving into a series of short internal solitary waves of very large amplitude, like 100 meters. So these waves are strongly nonlinear and non-hydrostatic, so they require fully non-hydrostatic numerical models. So more recently, you have some developments of this kind of model to explicitly represent these internal solitary waves, like in Sanchez-Guerrero or in Sanilo works. We complement here this list with the CROCO model. The non-hydrostatic approach had been presented by Patrick in the talk before, and it is based on the relaxation of the Boussinesque approximation instead of solving a Poisson system. It replaces the barotropic model solver by a fully 3D fast mode solver, resolving all waves down to acoustic waves. So this non-hydrostatic solver can be used in problems from a few tenths of meters to LES or DNS resolutions. Like Patrick said, it comes with monotonicity preserving advection schemes like Win5 or TVD, and fully 3D turbulent closure schemes. So it is a perfect candidate for modeling the straits and the dynamics of the Strait of Gibraltar. So my talk will review some interesting features of this NV2 module in the CROCO code. First, a 2D vertical slice model option, which can be nice for investigating some non-hydrostatic details. Then a fully 3D model option for quasi-LES and to go to the route to turbulence. And finally, the mesh refinement capability brought by the Agrif library for studying scale interactions. So I will start with the S2DV capability. And I will show that you can use a two-dimensional vertical section of the Strait of Gibraltar just to investigate some first order of detail for small-scale dynamics. So the proposed configuration is quite simple. It's computationally efficient, and it incorporates the configuration of seal characteristic of this region. So you can see here the grid along this blue line. We have 50-meter resolution on the horizontal, so it's x-axis, and 40 sigma level along the vertical dimension. The model features high resolution bathymetry at 100 meters, and we don't have any atmospheric forcing. We just put realistic stratification in temperature and salinity. And the model is starting with a locket change mechanism from initiative by Salini. Tides are adjusted within the CROCO Fortran code to fit values from the TPXO atlas. So after a 3-day spin-up, we run a 5-day run with a 1 second time step for the slow mode and 1/8 second time step for the fast mode. These are the keys used for this run, and I will show you once again here the importance of choosing monotonic schemes. Like Patrick said, you can see wiggles on the upper panel with UP3 and spline, and you have something regular when you're using a TVD. I think I have lost my presentation. Sorry, my presentation is out.
Is everything okay? Should we adjust something from our side, or?
I will start again PowerPoint. Yes, thank you for this. Just a few seconds.
Okay. Let me know if I should pull your slide up.
Actually, I have some videos in my presentation that you don't have on the slide.
We love videos.
Sorry, it's nice.
Yes.
Right. Should be okay. Sure. Yeah. So. Are you okay with the slides?
Yep, that's great.
Okay.
Yep.
So I was advocating for dedicated advection schemes such as TBD, and this is necessary here to remove numerical diffusion with such kind of simulation. So we compare in this slide two SDDB simulations: a classical hydrostatic simulation of the strait with 200 meter horizontal resolution, which is more or less the resolution of ocean circulation model there. And the other one is an NBQ simulation described just before. We have a particular focus on the shear instability occurring at Camarines Seal at the onset of the tidal outflow. So I present here the contour of vertical velocity in blue red with the isopycnal surfaces overlaid. If we look at the right panel, the NH simulation, you can see explicit primary instabilities that have been identified as Kelvin-Helmholtz instabilities, which are developing at the interface of the Mediterranean and Atlantic water masses. These instabilities are the starting point of the direct turbulent energy cascade, transferring energy from the large scale of motion to the small scale. And so obviously, you don't see anything like that in this hydrostatic simulation there. But this is not just a question of hydrostatic or not, or maybe higher enough resolution story. If you look at this picture, we show same kind of contours. This time with the y-axis vorticity in grayscale, still with isopycnal surfaces overlaid, and still at the same time the onset of the tidal outflow. So if we look at the NH simulation at 200 meter resolution, it does not feature shear instability. So this is not a question only of putting the NBQ CPP key. And if you look at this resolution, these two figures, this is not just a question of resolution. If you put 50 meter resolution in hydrostatic model, you won't have this kind of structure. So the message here is you have to set the NH physics along with a high resolution of the horizontal scales to have this way to the turbulence. We now have a look to internal solitary waves generated by the release of the hydraulic jump. In this lower panel, we represent the velocity fields and the isopycnal surface in white after 3 days spin-up. We can see a train of 4 mod 1 waves. Yeah. And the amplitude of the first wave can reach 100 meters. The Soliton train amplitude increase and exceeds 150 meters as it propagates over the slope in the Tarifa Nauru. Yeah. And then the wave amplitude decrease as it propagates towards the deeper region. Here we represent the depth evolution of this isopycnal surface as a space-time evolution diagram. Region of sharp horizontal density gradients can be identified periodically, like that. In the region of camarinal seal, and they correspond to the generation of hydraulic jumps. And the propagation of internal waves are identified by the tilt of the isolines, whose slopes provide an estimate of wave propagation speed. So you have mod 1 and there mod 2. Here we present the density anomaly fields in the region of Tarifa Nauru after 8 tidal periods. On the top, you have an hydrostatic simulation, and at the bottom, this is the non-hydrostatic simulation of 50 meters. This is a 220 meter resolution. And well, Patrick has already shown something like this. A wave train can only be identified in this non-hydrostatic simulation. In the hydrostatic case, the lack of non-hydrostatic dispersion produce internal waves propagating as bores. In this case, you have trains of solitons. So on this figure, we can show a comparison of surface slope in comparison with a SAR image from space. So as a conclusion of this S2DV capability, it is a nice and efficient way to make primary investigation on the small-scale features of the Strait of Gibraltar. This is a computationally efficient capability. The characteristic of the simulated internal waves compare qualitatively well with published observation and with previous numerical studies. And despite the shortcomings of this 2D representation, this configuration provides a realistic depiction of small-scale dynamics of the strait. So based on this work, we move on a full 3D model of the strait, which has been developed in the group with a horizontal resolution of 50 meters. This is a bathymetry here, and you have the same high resolution bathymetry at 100 meters. The lateral and initial conditions are provided by the Mediterranean system of ENEA organization. The tidal forcing includes 4 constituents, namely M2, S2, P1, and O1. And we still not apply wind forcing and nor atmospheric fluxes. And we made 2 days spin-up with the hydrodynamic version of the code, and then a 4 days simulation with the NDQ model. So here are the keys for this run. We have to define NBQ key, NBQ perf, select monotonic schemes, and include styles. So this is an animation of the vorticity field of surface currents. You can see several areas of hydraulic control of the flow here over camarinal seal and espartal seal. And then this is the control and the relaxation with hydraulic of this control with a jump. And you have the generation of internal waves each cycle, each tidal cycle, and they propagate here out to the main in the Iberian Sea. You have some reflection here in the coast of the waves. And if we look here, a vertical section of the camarinal seal, you have the topography and the surface elevation here. You have the tidal cycle here. And on this plot, you have the contour of vorticity in colors. The direction of the flow is in white arrows, and you have isopycnal surfaces in a black line. So this animation shows the evolution of an hydraulic control. Let's see later. Each tidal period and generated and relaxing an internal hydraulic check. So you have the control, which is starting here. And when you have the reverse of the flow, you will have the propagation of the internal solid hydraulic. So you have the control here, the jump. You have mixing here by shear instability. Jump to the active. And then the flow is changing, and you have the read of internal large. You can see this is 100 meter and more internal solid particles. So this 3D simulation allows us to investigate shear instabilities in the density flow west of the seal during the outflow. To do this, Margot Hilt has proposed a diagnostic based on the Q parameter, which has been presented by Patrick before. This is the second invariant of the velocity gradient tensor. And it measures the relative importance of deformation and rotation. When Q is strictly positive, rotation is larger than shear. And this is another animation of this Q parameter and this is its evolution for values of 10-4 in red. The temporal evolution of Q shows the oscillations. Yeah, you can see that. Wallets. And you can see shear layer here. Interface. This kind of structure are numerous between the Mediterranean vein and the Atlantic waters, and they are carrying westward by the Mediterranean outflow. And you can see this is a 3D structure. We have seen that the extension of the previous result for a 3D simulation, and we have some interesting results of shear instabilities and internal solitary waves from this 3D model. I will insist here on the new diagnostic that have been developed, such as the Q parameter for the detection of shear instability. And there will be also a new metric coming soon for the diapicnol mixing evaluation that is called BPE. So these new metrics are essential to evaluate the LES model and then go toward a better representation of diapicnol mixing in the ocean and in a climate model. This is the final part, so we'll see another important development in the NDQ module, which is grid refinement. We are using the iGraph library already used and presented in the CROCO hydrodynamic code. So briefly, we have introduced a two-way exchange for the NBQ variables as a fast mode. And we have tested it on the classical vortex implementation test case. This is a very nice experiment to test this. This is a baroclinic and asymmetric vortex, which is propagating on a beta plane. So in this test, grid refinement is implemented at the center of the square domain, and we look at the free evolution of the vortex. One-way and two-way nesting have been tested with this configuration, and you can see the surface evolution contour of the vortex from the parent grid over the whole domain, and with dashed isolines. And at in the child region, at the center part of this domain, you can see the solution by the nested model. You can see the continuity over the frontier of both solutions. So after this validation, the idea is to build a mesh repayment strategy for the Strait of Gibraltar, to include an area of intense energy transfer in the strait, and to upscale this energy to the large-scale flows such as tides or the mesoscale circulation. So the parent grid is a low-resolution grid with 900 meters horizontal revolutions. This is the Beer 4 domain in red that covers a wide area from Portugal here to Melilla with the Alboran Sea. And two child reads are embedded in this domain to finally go to 60-meter resolution compatible with previous results. Yeah, in this slide. So the first child domain is HR4 domain, and the resolution is 180 meters X and Y. And the second child is VHR4, and it is over the Camarine Sea. So to do this, we use the NestGIG graphical interface from the CROCO toolbox. We use same input field for the bathymetry, which is the same high resolution product presented before. Tiles are interpolated from the TPXO 9 multi-resolution atlas. Initial and lateral conditions are interpolated from the Copernicus Marine Service using both forecast or reanalysis. Bulk and surface fluxes are interpolated in this experiment from the GFS system of the NCEP. And finally, we use land and sea mask from the shoreline dataset from NOAA. So we in the GPTO project, we are evaluating the impact of this grid nesting between one or two domains in the NBQ approach. And we have performed a sensitivity experiment where we use no nesting, applying the NBQ module over the low resolution BR4 domain, with one child applying a two-way exchange, including update of the NBQ variable. This is the RIA 2 experiment. And when using two child domain, this is a RIA 3 experiment. So we are investigating the sea level as a first order large scale processing like tides, because tides are a direct driver of intermodal waves. And then we'll have a look of the surface current divergence as a proxy of special observations. First of all, so we present a sea level comparison here. Okay, sea level. For the 19th of October, 2020, sorry, during the Gibraltar campaign, we compare sea level from the BR4 and RIA 2 models with respect to near real-time observation of sea level. So observations are provided by the European Union for Sagres and Albufeira stations, which are in Portugal, and by Puerto del Estado for Tarifa station in Spain. Model sea level anomalies in blue, and observation are in green. So for Sagres and Albufeira, we can see a time lag reduction brought by the inclusion of the refinement. From here to there. And for these two stations, we can see also that the tidal amplitude is lessened in this RIA2. So these two elements combined in a reduction of 10 to 15 centimeters of the root mean square error, from 45 centimeters to more or less 30, sorry. This root mean square error reduction is mainly due to the time lag reduction. In Tarifa, you cannot see this loss of variability, but the time lag with respect to the observation increase. If we compare now RIA2 and RIA3, so when adding a second embedded child over the camarinal seal, you can see RIA3 on the right, and we have an increase of the model sea level variability for Albufera and Sagres station, leading to a root mean square error reduction of 50%, from 30 centimeters to 15 centimeters. So in Tarifa, there is no significant change from the time lag when adding this zoom. So this gain in energy, when you can, when looking at Sagres and Albufera station, maybe the expected sign of a better transfer of energy to the internal modes. It can be, it has to be diagnosed. These two figures illustrate the divergence of the surface current in the Strait of Gibraltar as a proxy of surface rugosity retrieved from the synthetic aperture radar observation. Still at the same date, the 19th of October 2020. This figure illustrates the divergence of the current at the intermediate resolution, 200 meter resolution. If we compare the both system with two-way nesting, we can see more fine scales over this region of the camarinal seal, and more intensity in this RIA3 model than in the RIA2 model. You can see minor differences in the two models on the pattern of the internal solitary waves at the eastern end of the strait. Maybe due to an advance in wave propagation in this RIA3 model. If we present here now on the left the results from the BIRF model, the same divergence of the current. And here, this is the low resolution. This is the parent field from the RIA3 model. So this is the same resolution, but you don't have the same physics because you have upscaling of all the two-level childs in this field. And thanks to this successive grid refinements, allowing to downscale to the earliest resolution, even at low resolution, this parent grid exhibit more fine scale and more energetic at the surface than this just low resolution model. And you can see that once again, you do not have the same pattern of the wave propagation at this eastern end of the strait, and this is the good pattern we can observe on observation. So, in conclusion of these studies and this presentation of this NVQ module, this module for non-hydrostatic simulation is ready for realistic run, even in a near real-time run. It features an enhanced physics for LES and DNS problem and nesting capability for studying scaling interactions. Of course, we still need to validate, and we need observation to validate all of these findings. And this is object of the analysis of 2 fringe campaigns in 2020 and this year, last month, in 2022. And our investigation continue over the Strait of Gibraltar, in particular on large-scale upscaling of this small-scale dynamics, in studying also the diapetnal mixing properties and with some new feature in the interaction with the atmosphere. From a development point of view, the future evolution of the NVQ model will concern the surface inner ocean hydrodynamic, non-hydrodynamic coupling, the bottom interface condition for acoustic gravity waves as well, and some physical and numerical acceleration of the code. So this is my conclusion, and if you have any question, let me know. Thank you.
Thanks a lot, Laurent.
Yes.
So people, do you have any questions there?
Okay.
Let's have the question.
Yeah, there is a question on the chat from Nicolette about the computational power needed to go to this kind of scales in terms of computing powers, number of cores, and so on, in terms of data storage also.
Yes, it costs a lot. It costs a lot. For instance, this grid refinement with 2 childs, it is 50 gigabytes of storage when you archive with enough resolution, time resolution, because you need a high resolution of the grids, but you need high samplings of the result to see the evolution of these processes. In terms of computational cost, it is 2 hours of run for 1 day of simulation, and these tests are using 1,040 processors. You can it is quite scalable, so you can run with a 200 processor, and it will cost 7 times larger of time.
It's also why we're scheduling to go on GPU and so on.
Yes. You don't need also all the full non-hydrostatic physics in the parent grid, so you will have some gain like that. We are working to improve this computational cost. That's why also you have this section, this vertical section option, you can have a full resolution and for a nice investigation of some propagation over a shelf. You have a transect, a vertical transect, and you can first investigate with a cheap cost. Of course, this is not 3D, and you have the defaults of this is not 3D. Depends on the problem.
Okay, thanks. So any other question? All students are lowering their eyes. So. I think no more questions. Thanks a lot, Laurent, for this presentation.
Thanks to you for the invitation. And have a good afternoon, good lunch, and good afternoon.
Yeah, thanks a lot.
Thank you. Bye.
So people that are on the schedule for this afternoon about non-prosthetic, I think they will turn down less remotely. I think there are academic cases like Soliton and so on. And you might also consider what you are doing. I don't know if there is lunch or I know. I don't know.